Thank you, Ken, for the invitation, and I want to thank everyone for your warm hospitality, actually. This is my first time doing science in Asia, and this is the first ever stop I made in this trip. So this is super exciting, and I want to thank you all for welcoming me here. Is it loud enough? Can people from the back of the room hear me? Great, okay, I'll try to project as much as I can. So 3 years of searching for the most distant galaxy, and what have we learned so far? I've made this mistake many times, and it sounds like I'm going to summarize everything that happened in the field in the last 3 years. No, I can't do that in an hour. Okay, not everything, not a collective we, just me, basically. What have I learned so far, or the SAM group, or the high Z people? A few of us. So the background you're looking at here is actually a little portion of the SEERS field. SEERS stands for the Cosmic Evolution Early Release Science Program, which is one of the first programs for JWST that was selected way back in 2017, and it's meant to partly develop the JWST reduction pipeline for the community, but also get the whole community ready for this beast, this new instrument. So it's a brand new instrument, it's a brand new program, and it took us a long time to get from zero to having something like this. And we're incredibly lucky with this because this image was taken within the first few days of JWST scientific operation. It was taken actually back in June, and it's embargoed until July, and it's been released as the first batch of data along with everyone else. And because we are one of the early release science programs, so our data is public right away with zero proprietary time, so everyone in the field have something to scoop from. Just kidding. To work with. This is the whole point for ERS program. We also develop the things, the tools for everyone to use, but the data is for everyone, so no one has to wait a year to get to the data, and then they can go on and do the data reduction themselves and also get ready for cycle 1. We have JWST for God knows how long, probably a decade and plus, but back then we didn't know. So getting the field move quickly and get everyone ready for this kind of science is really important. So I've been showing you this black screen the whole time. What am I doing? There's a lot of interesting thing in there. So what we did in the first few days was just, reduce the data, create this colored image, but just go around, zoom in, and look at interesting galaxies, and I encourage you to do the same thing. So you can go onto the SEERS website, download the full resolution image. It's just 284 megabytes. It's not that big. Just open it up and zoom all the way in and find your favorite galaxy. And it's really, really fun. So we're really lucky for that. And the value for this type of extragalactic survey is really, it created a chocolate box full of galaxies, and with all sorts of different instrumentations, survey modes applied to these fields, so that everyone, 150 people in the SEERS collaboration, everyone can find something for themselves. So the collaboration has been incredibly productive in the past few years as well. Great, so this is the rest of it. We got the second half of our program in December, and this is the full SEERS field. So this is public, and I want to take you on a journey, and let's fly to one of the most distant galaxies we found in the first few months. I wish there's a way to speed this up, but I can do some narration over this. So, oh darn, it's red. Sorry. I blame your projector, but so the fun thing you can do is, this is not precise distant measurement, but just by their colors, you can measure how far away these galaxies are, roughly. But then with some computational magic, we can now sort of do a little fly through the field, so you can see you're flying further and further out in space, and now there are galaxies that are really far away, but you also realize the universe is getting a little more quiet. There are fewer and fewer galaxies in the background. And finally here we arrived at probably redshift 10, where you're standing at right now, and you're looking at a galaxy at redshift 12. I'm talking way too fast. Here we are arriving at this galaxy dubbed the Macy's Galaxy, which at the time when we found it, we first thought is at redshift 14, and later we revised our photometric redshift measurement to estimate to about redshift 12, and the spectroscopic measurement is about redshift 11.8 or something like that. So it's not too far off. And by today's standard, 2025, this is not the most distant galaxy, but this already easily has broken the Hubble limit of redshift 10. It went way past it, so which is amazing. We found one like almost right away, so is everyone else. These galaxies are everywhere and all over the place. That's a pleasant surprise for us. Now I'm pretty happy with this. And I want to talk to you about another program as well. This is called NGDeep, the Next Generation Deep X something public survey, something like that. So this is one of my favorite programs. It's our Cycle 1 program, which it still is, I think, one of the deepest field we have image with JWST. This is just one JWST near cam pointing. You can recognize it by the instrument chip gap in between. So we have two detectors on near cam. This is the near infrared camera, the main camera in JWST. So this is just one pointing of the telescope. We just point it at one location. And then we take a really, really long exposure, and this whole image took about 122 hours to epoch. We took it over the course of two segments. And this is so deep that we can see a lot of galaxies in there. But one way for us to appreciate these images is really to do a little blink back and forth with past imaging with Hubble. So it's not to put Hubble down. Hubble is great, but this is meant to be transformative. This is building on the success of Hubble, so we can propose for a next powerful space telescope and put it in space, and now this is the result. You can see this is JWST, and we blink over to Hubble. You get a little more infrared color. JWST goes a little further down in mid-infrared, and well, this doesn't have mid-infrared, but it also goes further down in near-infrared as well. And then a lot more of these background galaxies pop out. But also look at the big extended galaxies. The details of the galaxy also pops out, which enables all sorts of study. For example, if you have nearby face-on galaxy, you can study their dust tracks and their structures and everything. But also bar structure, mergers, morphologies, all sorts of things that we couldn't do at very great distances. So JWST is really an incredible machine. Usually I have a slide that summarizes all the Sears and NGDeep exciting papers that came out, but then I stopped doing that for a while. But I still have those slides, so do talk to me about your interest in science, and I will point you to the right Sears and NGDeep papers. I want to dive right in because I have so many more slides to go. So the huge elephant in the room at the time of these observation is that JWST really surprised us with a lot more galaxies at redshift 10 and above. Within the first billion year of the universe, or within 500 million years, there are a lot more galaxies than theories have predicted. This is observation, the gray band. The theory, the simulations, those are all the colored lines, all different simulations. And yet, oh, by the way, this is mine, purple arrow. Right down the middle, it's not just my problem, it's a problem from all of us. None of the simulations out there are predicting as many galaxies that JWST have seen. Now this is troubling, but let me also explain this a little bit more. This is a cumulative count of objects for objects greater than a given redshift, integrated over time, over distances. So what you see here is, for example, as redshift 9, that means the number of objects we expect in the field that are at redshift 9 and above all of them. So the fact that these simulations do not match the observation at redshift 9 just means that we have fewer objects over the course at redshift 9 and above, not at redshift 9. Yes?
How about everything?
We'll get there. Well, it's a toy model. It's a toy model that, well, first, the mismatch actually mostly come from the fact that most of these simulations don't have galaxies at redshift 10 and above. So they have very few galaxies. The sample is incomplete in the first place in these simulations, so the integrated count is lower. So Baruzzi and Silk is a toy model that go all the way out to 15, so they have the advantage of actually having galaxies out here in the first place, so you can start integrating and counting properly. But also, it's a very simple toy model that assumes that the halo accretion rate and star formation rate would increase beyond redshift 9 the same rate as they used to between redshift 2 to 8, something like that, right? So it's rely on a simple assumption, assuming this rate will increase the same way, but we kind of know it's not really physical. Stars has to take, there's a delay between gas being accreted onto a halo and before they can form stars. Okay, so bummer. What do we do with it? Let me take you back in a few years, back to 2017. This is like a little talk in the talk scenario. So I used to give this talk called Paving the Way for Future Space Telescopes with Theory and Simulation. There are many kinds of simulations out there. We are very familiar with these numerical simulations. Some of them are really big. You can cover a cosmological volume, but they are not high enough in resolution to capture baryonic physics properly. And then idealized galaxies, Chaoyu and Ken knows very well. These are very high resolution, and we love them. We learn an incredible amount of physics from them. But the problem is we don't really have a statistical sample with these type of simulation. It's really expensive to run just one. Maybe we can run a dozen, but we can't do 1 million of these. I wish I can. We just can. So the tension really is how many particles can we fit into a computer, quite literally, physically. And we can either do a big volume with very few low resolution, or the opposite. But we can't have both. We can't have a big volume, large galaxy sample size, and also have all the physical details. It's just not possible. So I'd like to introduce another axis to this plot. There are different kinds of simulations out there besides the numerical methods. So going vertical now, the top of the page will represent simulations that are, have higher physical fidelity, being more predictive, more useful, but also intense computational, require a lot of computational resources. But as we move down in these different types of simulations toward the bottom of the page, models become more and more empirical, which means it relies on available observational constraints to build this model, and they become less predictive because it builds on the things that we see. We try to match them. But at the same time, these models are, more efficient. So it's great for building big catalogs. People do this all the time. There are HOD models. There are subhalo abundance matching that you probably have heard of. So what we do is that we pick somewhere kind of in between. We want to have something that is still physical, but not prohibitively expensive to run when we need to generate predictions for millions of galaxies. So the method I've been using or doing my work with is called semi-analytic models. And let me dive into a little detail and show you how it works. Yeah, I don't have nice pictures. That's all the nice pictures you saw. Now just hardcore text pages from now on. So SAM is a way of trying to model a large population of galaxy and model their bulk global properties by solving a bunch of differential equations. So we start with the dark matter halo and their merger history. We extract how a dark matter halo formed from numerical simulations. And then we write down a bunch of analytic equations and figure out what the baryons are doing over time. For example, we start with halo. And then just by multiplying by the baryon fraction, we can already get the amount of hot gas inside this halo, inside the halo. Now, through various cooling mechanisms are shown in yellow, we get from hot gas to cold gas. And then we also have a recipe for multi-phase gas partitioning, which we partition the cold gas into multiple species of hydrogen. And from there, we use molecular hydrogen as a tracer for star formation activity, star formation rate. And then a few things happen once we get here. Star formation can introduce feedback that reheat some of the cold gas and make it hot again. And some of these cold gas will even get ejected to the halo and later reaccrete back as hot gas or get ejected forever. And then can also now properly integrate that and get a stellar mass out of these galaxies. So this is a little simplified still, but I like to use this as a little tool to explain how a SAM works. So it's highly crafted. It's not as natural as a numerical simulation, but it's still a great tool. It's being super efficient and also modular, so we can do a lot of experiments with it. We have full control over what goes into a SAM. Okay. And it's great. So we can now predict a wide range of physical properties of these galaxies at a very efficient scale. We can do millions of galaxies overnight on a laptop. That's how efficient these are. And yet remain physically motivated. But beyond these physical properties, we also forward model the full star formation history into synthetic stellar SEDs. And then we also add dust attenuation, IgM attenuation, and other effects, and have them convolve from rest frame UV or another band's luminosity into observed frame luminosity. So now we go from a physical model with dark matter, things that we cannot see, down all the way to things that we can directly now measure with a telescope. Again, there are assumptions went into these. We're aware of them, but there are things that now the community can use. So the model performed actually quite well. We have been accused for having too many knobs in a free model like this. You can tune your model and have everything match. Well, it's not how it works actually. So we have free parameters, so as every model, but we only tune our free parameters, the physical parameters, once at redshift 0. Well, every model requires some calibration. But then we let physics take its course and we let the predictions go. And then we look at the higher redshift universe and see if these physics that we include inside the SAM, are they enough to explain the evolution as they're observed in the real universe. So the data points here are stellar mass measured from redshift 4 to 8. So these are stellar mass functions. If you're not familiar with this quantity or this type of plot, the x-axis marks stellar mass, and then the y-axis practically marks the number density of galaxy we expect at a given stellar mass. So this is a distribution function. And the model is quite successful at reproducing the evolution up to redshift 8 at a time where we only have Hubble estimates. So this is pre-JWST. And it does the same thing with the distribution function of star formation rates measured by Hubble and other ground-based telescopes. And we also can reproduce the UV luminosity function, so this distribution of galaxies by UV. So the model is actually performing quite well all the way up to redshift 10. So that goes back to my point earlier. The models do match observations at lower redshift, but at redshift 10 and above, there are just no constraints. So there is completely unconstrained, and many simulations don't even bother to go that far. And our simulations went further, but didn't produce as many galaxies as we saw. So it's the Wild West. Another thing I want to point out is we do also have 2-point correlation functions predictions. So these are the spatial distribution of sources and how clustered they are. You can imagine the bottom of each panel marks a random distribution. If the galaxy's distribution across space is fully random, then you get a flat line that goes down to the bottom of the page or of each panel. And the further up they are, the more clustered these galaxies are at a given separation in pairs. Anyway, so there is no knob to tune these. It's not like the star formation recipes that I talked about earlier. This is the distribution of halos, underlying halos, but also galaxies we put in there. But the fact that the SAM is able to naturally reproduce a lot of these early measurements of the 2-point correlation functions all the way out to redshift 7, it's quite surprising. So I like this, I put it in, and this is why we have a lot of faith in these predictions early on and use them to do a lot of exciting prep work. So this whole series of work was dubbed the Semi-Analytic Forecast for JWST. I started it as my PhD thesis, but it went way beyond that. So I did the rest of it during my first postdoc in NASA. And this is a mock light cone. So this is a cone-like structure that we just sort of arrange galaxies into in a way that it represents the universe that we see. And I always forget that there's this nice animation that we make with my last NASA press release. So this is a big light cone I made for the Roman Space Telescope. And you can see this is a way of mimicking how we see the real universe. You can take slices out of it, and it will look kind of like the real universe with large-scale structure and everything. So the clustering kind of reproduce what's in the real universe. And this is the kind of tool we supply to the observers to use and plan their observation program. So let me just talk about one more thing before I dive back into what have we learned in the past 3 years. Theory plays an important role in designing this type of survey. We always start with a theory and model and observations that and simulations that is rigorously tested, meticulously crafted. And then we go from there to an idealized simulated field. You can't do that with a simulated box. You have to make it into a light cone. So we can flatten it into a field that kind of represents what we see with a telescope, right? Things closer to us are older, things further away from us are younger. So we have to have that information encompassed in there. So this is already an extra step towards the observing community from the theory point of view to make things useful for them. And then there is synthetic observation. We try to also then make the idealized simulated field a little more realistic. We try to inject instrument noise into it. We try to make it smudgier. We try to piece in real galaxies based on what we predict. Do a little matching from the candle's noiseless images, so that we can use these type of synthetic data to practice data reduction and see if we can even recover what we put in a more controlled environment before we deal with the real thing. And this is all done years before JWST was launched. And then from there, we can now use that to optimize survey strategy. We can now use that to forecast the outcome of survey programs like SEERS. How many galaxies are we going to get? Do we go deeper or do we go wider? Can we write a compelling proposal to convince the tech to give us another 300 hours? That sort of thing. So this is important. And then finally the real observation arrived and they tell me I'm wrong. Which is fine, Then we build the next sort of model and the cycle go over and over again. But theory plays a really important role in making progress alongside with other things as well. Okay, so I just walk you through the whole process of creating this type of simulations. Every group does something different, but here we are. Not enough galaxies. What do we do now? Well, here comes the first point we learned. A physical model that well-reproduced galaxy populations at redshift less than 10 are not sufficient to explain the rapid star formation at redshift greater than 10. I know. It's actually 0.0, but keynotes won't let me use 0 as the first counter. Bummer. Okay, so get back to work. First, we need to know how halo form. As I mentioned earlier, SAM, this particular modeling method, rely on dark matter halo merger trees or their assembly history, how halo emerged in the early universe as input. We need to know how that works. The problem with that is we don't have it at this redshift. And as I mentioned earlier, most simulations do not go that high redshift because it's difficult. So these are three kind of well-received simulations out there in the pre-JWST era, if I may. So VSM-DPL and Bouchard-Planck are both from the multi-dark suite. These are really big boxes, couple hundred megaparsec on the side, very huge volume. Pretty representative of the real universe. But the problem is, if we want to model a redshift 15 galaxy, we need merger trees that go well beyond redshift 15. We can't work with just the halo at redshift 15. We need to know where they come from. And the fact that Illustris only has 14 snapshots from redshift 4 to somewhere 20, and then Bouchard-Planck gave me 29, VSM-DPL seems to be okay, but it also kind of run out at 26. It just doesn't give me anything I can work with. So I took matters to my own hand and created the graph simulation where I stored 171 snapshots between redshift 6 to 40. And this was actually done in 2019, which before JWST was launched. I just did it right before I graduated, so I have something to play with after I leave the CCA. And it turns out to be something super important and will serve me for the years to come. So the nice thing about, well, I just have to explain what graph is. So graph is, it stands for gadget at ultra-high redshift with extra fine time steps. So the name says it all. It's based on gadget, the gadget 2 code. It focuses on the ultra-high redshift space. And then it has very, very fine time steps. So most simulations, as you can tell, they store finer and finer snapshots at lower redshift because that's where most of the simulation are interested in. But at higher and higher redshift, because most of these boxes run out of resolution anyway, so they do not have to store as many snapshots out here. There's probably nothing for them to store anyway. But for us, we care about the actual merger events at these redshifts. So our time step has to be really, really fine so that we capture the merger shortly after it happens instead of having this very jumpy snapshots, and that will probably give us some 5-way mergers that is unphysical. So at the very high redshift, we have snapshots that are only 1 million years apart, which is very crazy. Okay, so that's something that we can work with. So as I mentioned earlier, you can't have both resolution and box size. It's not possible. You can't do that. So, but galaxy at the early universe is really hard to model because they are both rarer, which you need a bigger box, but also they are lower mass, so you need high resolution. So whatever you cannot do at redshift 6, it's even harder to do at redshift 20. right? They're both smaller and rarer, so gotta resolve them somehow. So what we do is we, instead of doing this in one huge box that is prohibitively expensive, we do that in 4 chunks. We did it in 4 boxes. The idea is that we used 4 boxes to patch over the mass range that we're interested in, but we simulate a given mass range at a time, so that we have the little branches of the merger trees, so we can later graft them together. You know the gardening technique, grafting. You take a branch, you stick it into a different tree, it keeps growing. That's grafting. So graft is a homonym of the grafting method. So that's one way we plan to build bigger merger tree at low cost in the future. But the surprising thing is, just by running the same SAM, the same physical model on this new merger trees, we are already getting more galaxies out for free. Whoa. So what we're looking at here is the purple line is new predictions with graphed, and then the cyan line, the lighter cyan line, is our older predictions with extended press structure merger trees. Those are statistical merger trees that we generate based on analytic mechanisms. And those are not really tested at this regime, so we used it because it's available, but because we didn't have anything better to use at the time. So you can see at redshift 9, yes, we get more galaxies, but as we go on in higher and higher redshift, extended press structure really failed and predict very few galaxies, but our model is actually making stars. It's capable of making stars all the way out to redshift 12. It's still kind of on top of the observed data points or the reported number densities, but at redshift 13 and 14, yes, we do run out of galaxy. We're not that good at making stars in the early times, with our old model. This is already a big plus. So just by getting the merger activities of the underlying halo right, we increase the amount of starbursts induced by mergers, and that already gives us a lot more stars. And this is cool. No one has seen this. So capturing the underlying dark matter halo merger tree is useful. It's really important for modeling galaxy at this redshift. That's another thing too that we sort of learned early on after the discovery of these galaxies. Now this might get a little more tricky. So I'm in the first kind of fast response paper we put out. This is the first paper I put out in the post-JWST era. A lot of colleagues were jumping out and say, the universe is broken because we can make these galaxies that fast. Lambda CDM must be wrong. And we're like, wait a minute, not so fast. There's still a few things we need to consider more carefully. For example, one thing that we haven't talked about enough is cosmic variance. These fields are small. They are just tens of square arc minutes wide. Sorry, it's a theorist. I've been saying megaparsec the whole time. But square arc minutes, like these are small fields. These are not representative of the real universe. These number counts can vary from field to field to field to field all the time. So if we add in this colored bar here that represents the variation due to cosmic variance and add them back to the regular error bar to get this gray bar, you can see that the gray bar can, the error bar can grow quite substantially, especially at the early universe. After we add in the color bars, yes, we just can't conclude the number density from a tiny field from these observations that early on. Remember, this is probably within the first few months, within the first year or so. All the things we compare to are 23, 24, 22. So this is within the first year of JWST operation, and we don't have as much data as we have today. So that was really important. Another thing is photometric redshift uncertainties. The fields are small. So to get number density estimates, we have to combine galaxies across a wide redshift range, but also partly because these are all photometric redshift. So you can't quite tell exactly what redshift they're sitting at. It's just, within this range somewhere. So for example, these data points on the left panels, these programs are reporting the luminosity function as they are at redshift 11, but in fact, they contain objects all the way from redshift 9 to 12. So the redshift 9 luminosity function sits all the way up here, and the redshift 12 sits down here. This is a huge range that is not really being talked about at that time. So we also throw these out here and say, well, if most of those objects in those bins are redshift 9, then we don't have a problem. right? Because our redshift 9 galaxies are there. We predicted those. But if most of these objects are at redshift 12, which is unlikely because by distribution there are just fewer of them, then we'll be in problem. But that's a problem that we need to figure out. We need to figure out exactly what redshift these galaxies are at. So that's something more to talk about. Okay, so top-heavy IMF is another interesting one. Who doesn't know what an IMF is? These are initial mass function, a huge caveat that goes into all sorts of simulations and SED fitting code and everything, right? We assume that the initial mass function of stars are universal, is unchanging, and the same everywhere at all time, everywhere in the universe, just like the cosmological constant. No, it's not. So there are good reason to speculate that the initial mass functions are different at the early universe, and very likely that the stars are brighter. So we didn't really go into mess with the IMFs, but we are just making a very simple assumption and say, what if the IMF is different and galaxies are somehow brighter, stars are somehow brighter? By a factor of 2, by a factor of 3, by a factor of 4 out to 10, that gives us these shaded regions. And you can see that, yes, it can boost the number counts in the luminosity function space by quite a lot. So that's another thing that's been not been talked about, but just by looking at the first stars paper, simulation SED papers, getting a boost from 2 to 4 times is not crazy. That's the typical range. 10 is a little bit of a stretch, but probably 2 to 4 is all we need, and it's reasonable. And one more thing, this is also important, and a lot of people are working on this actually, a lot of people, is the UV variability of stars. So star formation can be bursty, right? It's not a constant process that's unchanging over a course of, you can average it over a course of a million years, but down to the time scale of tens of million years or even below, star formation can be pretty bursty. It can be temporarily getting a UV boost when star formation is active, and then it goes fainter when star formation is getting, subside. So if we add in a little scatter, a little sigma around our UV luminosity, that can also result in a boost in the luminosity function because of the Eddington effect. It's a lot easier to boost the luminosity function, the distribution function to the right, just because of the log scale. By adding a scatter, making a few objects temporarily brighter can already fill these more luminous spins to the right. So that's the amount. The more scatter you put into it, the more apparently the luminosity functions get boosted. So that's another thing that a lot of people are looking at and try to use that to explain why there are a lot more galaxies we see today. Okay, so where's my fourth point? Oh no, that wasn't a fourth point. Oh, that was my third point? The uncertainties are underreported, yes. So I just show you that there are uncertainty not just in simulations. Of course, the cosmic variance is one thing. The photometric redshift is one thing, but I'm also pointing the finger at the theorists. The IMF is another thing that we need to really deal with. UV variability at this short time scale is also not really characterized at these redshifts. So another thing to look at. So something we learn. Okay, now back to this. I've gone 3 points into it. I still have not addressed the discrepancy between the observation and the number count. Oh, am I even going to solve this? How much more time do I have? I'm about halfway. That's good, that's healthy. Plenty of time to talk about the future. So we've been pondering upon ourselves, what's missing in the SAM? The nice thing about the SAM is it doesn't take a year to run. Right, we can just throw something in there, we can run it, and we can see what comes out and ask ourselves, is it physical? Does it mean anything? And it's not just us, but also other people are trying to come up with different ways to explain what might be going on in the early universe. Don't look at that yet. So around this regime, what is special about these galaxies that is not in the lower redshift universe, so that we as theorists can just throw something in here that changes these galaxies, but do not change any of those galaxies earlier. That's kind of the goal, actually. Well, so Afshai was proposing this mechanism called feedback-free star formation, which was actually kind of pioneering what we do. It's very early on, once we have that discrepancy in number density, then Afshai came out and say, maybe stars form inside a cocoon so that when they explode, the pressure from the inside can cause a second generation of star formation in the shell of that cocoon, and the shell will also shield the rest of the galactic star forming disk from feedback. Remember, strong feedback can just kick out all the gas, and there will be nothing left in there to form more stars. So feedback-free star formation that I just described was one of the earlier story that we tried to tell and test and see if we can use that to produce more stars. Well, it worked really well in a toy model situation. So a simplified limited SAM where we only test one or two single component or quantities, but it doesn't work well in the full SAM because a lot of things are going on in the full SAM. So if we put in feedback-free star formation, then it has to do with the density of the cloud is not really doing what the toy model, the assumptions that went into their toy model, and there are a lot of things that has to do with the halo spin and the spin of the galactic disk and stuff like that. So, well, also tomb ray Q, the disk instability and stuff. So a toy model can be a good place to start, which we do all the time. But when it's being implemented into the full SAM, things can sometimes not work out. So that's one of the I guess, just the storytelling or small talk I want to get across. So we came up with something else a few months later. This is what Rachel Somerville dubbed as cloud-based or cloud-scale star formation. And later in the paper, we called it density-modulated star formation efficiency. So the idea is star formation can be more efficient inside gas clouds, in molecular clouds. And we see that in nearby universe. We see that in the SMC, and there are clouds that are forming stars. Now the thing is, what if the star formation efficiency in these dense clouds are just higher? Maybe we can use this as a way to form more stars, especially in the early universe. We know that these galaxies are more compact, are denser, and the star forming disk is also denser. So we can just come up with something we need something that is grounded. So there we have the star formation efficiency inside the cloud as a function of the cloud surface density. So as the cloud get denser and denser, or as we looked at more denser clouds, star formation efficiency are higher. And for clouds that are not as dense, the star formation efficiency is not as high. So toward the left, we have observational constraints from the GMC, and then for the rest of the curve is guided by these high-resolution idealized gas cloud star forming cloud simulations by our colleagues at the CCA. And then here we have the lifetime of the cloud versus the cloud surface density. So the idea is the faster these clouds form stars, the quicker they run out of gas and they die out. So that's the idea. Now, so we have written down a few of these relations, and then we basically have a free parameter called the clumping factor, and then we use that to approximate how much gas is being trapped inside this gas cloud. And from there, we can model the star formation rate just by having the cloud formation, star formation efficiency multiplied by the mass of the cloud versus the time they will run out of gas. And then from there, voila, we have a star formation rate that we can work with. A star formation rate that is modulated or boosted by the presence of gas clouds. So the idea is we tested a few free parameters of the model parameters. So the one parameter that we play with here is called F-dense. It's the fraction of gas that is trapped in dense cloud. So when F-dense is 1, that means all the gas is being trapped in clouds, which is not physical, right? You can't have a disk that is just a bunch of clumps with nothing in between. So that's just an extreme scenario that we try to play with, but this is the highest it goes. All the gas in the cloud, in the disk, is stuck in cloud somewhere, somehow. And then there is a scenario with 0.5, which is the red line there, which half the gas is in clouds and the rest are just distributed in the disk. And the last one is what we think is most realistic or most probable, it's just 10%. All we need is 10% of the gas being trapped in cloud, and the rest are distributed in a regular galactic disk, just like any other galaxies that we see in the lower redshift universe. And you can see out there at redshift 6, the models are doing similar things because the galaxies are not as dense. The cloud mode of star formation is not really kicking in, which is good. That's what we want to see. And the yellow line there is an extreme scenario where we test out, which we just turn off stellar feedback. So a galaxy gets to just keep all this gas. We would like to form stars, but there's no feedback, which is not physical, but we just put it in there as, you know, an illustration of the extreme scenario if all the gas is allowed to turn into stars without feedback, without any tool. What would happen? But just by looking at the 3 red family color lines, you can see that they converge at redshift 6, and they agree quite well with our older pre-JWST model labeled KS, the cyan line. But as we go to higher and higher redshift, when cloud mode kicks in, these models start to diverge, and at higher redshift, really, the more gas being trapped in clouds would yield more gas, more stars, and this is expected. This is what we it's like the sanity check. This is what comes out, which is good. Now we have the ability to make stars fast. So at redshift 12, we can make a lot more stars than observed. And at redshift 14, we now have a model that sticks on top of the observed lines. And at redshift 17, yes, even this extreme redshift stuff, we can still somehow make them. So this is still just, you know, in the middle of developing the model, because we're not allowed to tune this model halfway through the simulation, right? So these are clearly 3 distinct scenarios that we can't quite stitch together, but I'm just demonstrating that we have the ability to make galaxies that quickly. So now we have another problem. How do we get from redshift 17 that requires all the gas inside clouds down to redshift 11, which we only need 10% of the gas being trapped in clouds? Well, that can evolve, sure, but we don't want it to. It shouldn't. It's physics. Physics shouldn't evolve. So I want to go back to this space, the space that we saw earlier, the number density of galaxies in the field measured by Sears and NGD that you heard about at the beginning of the talk. So we have our pre-JWST model where both at the shallower depth and the deeper depth, they're both well below the observed number count, which is the problem. But now we have sort of the cloud FD1 model that is pretty good at reproducing the observed count out to redshift 13-ish. I would say I'll give myself that. And then beyond that, we probably need something closer to cloud FD5, and then cloud FD1, we just don't need that much gas overall. It just overproduced the count at all redshift. One more thing. So this is not exactly the same plot, but we dive into this a little more and realize the solution was actually lying in front of us all the time. So what we're looking at is the solid line, not the red line, but the solid brown blackish line is what you saw earlier. This is for the cloud FD1.1 model. So the one that I deem more realistic, that reproduces up to redshift 13, but then falls short at redshift 13 and above. And the dashed line is what we get if we add dust. Galaxies are dusty. You know, they are dust. We have not talked about dust this whole time. We're sweeping that under the rug. Well, we did talk about this in the paper, but it's a 1 hour long talk. So there is dust, and it will make galaxies a little fainter. But there's also the UV variability that I mentioned earlier. Galaxies can be temporarily brighter. And if we put in a little scatter around our galaxy population, based on some other numerical simulations finding, then we get this little boosted dotted line from the solid line. So there are 2 things going on this plot. One is dust that brings it down, and then there is starburst that brings it up. And these 2 mechanisms don't work exactly. At higher redshift, we have fewer dust. Those galaxies are better at making stars, and the assumption is when star formation is high, dust get ejected as the star forms, so dust don't really accumulate inside a galaxy. This is from Andrea Ferrara's little toy model that came out also shortly after JWST observations came out. And then we expect starbursts to play a bigger role in the earlier universe because these young galaxies are forming stars really rapidly. So at the early universe, we think there's a huge boost from starbursts that will bring us up, even with our most physical model that's falling off the chart. With that starburst, we should be fine. Of course, dust will take it out a little bit. So let me backtrack a little bit. The red line here is when we combine the effects of starburst and dust. This is what we get. So in the early universe, we get a lot of boost from young stars, from the burst. But then as we move further and further down to lower redshift, the boost from starburst string a little bit, but the effect of dust attenuation also kicks in and take out a bunch of galaxy, so that we have a little boosted scenario in the early universe and a little push down, flattened scenario at the lower redshift. And now we can reproduce the observed constraint without the need to fiddle with the physical parameter. It's still the same Cloud FD.1 model. We don't need to fiddle with that, which is nice. I like this. This is another thing that we learned. Fourth point here. We have to update our star formation recipe. It's not completely unhinged. It's grounded by some local observations and high-resolution cloud star formation simulations. But we also need the effect of dust attenuation and starburst to play in tandem so that we can explain the observed evolution. It's kind of flat. It's kind of hard to explain why the observed number count is so flat. It seems to be unevolving over time. And now we have a little story to tell about that. So that's fun. How much time do I have? I find exhausting just explaining this whole thing. Breaking news, more galaxies, shoot. So this came in this March. Some of our colleagues are reporting galaxies, well, galaxy candidates at redshift 17, 25, 30, and 32. So this is the number density count that comes out. This is actually UV density. It's very similar to what we saw before. But you can see this is not just flattened, it's straight up, there's an inflection point. Well, whether these galaxies are real, I do not know. So this is what they look like. These are the dropout bands imaging in JWST. You can imagine today is the JWST Cycle 5 deadline. So if you're really inspired, you still have time to write up your own proposal and do follow up on those. But I'm sure not just my colleagues, but everyone, a lot of people out there are writing their own proposal to follow up on this. So maybe in a few months, maybe in more like a year, we'll know what redshift these galaxies sit in. But for now, for the sake of this talk and the work that's been done, yes, these galaxy candidates are candidates and still remain candidates at this point. And let's treat them as real. And still ask the question, do they break the universe? Okay, so let's bring back graph. Graph is useful in many ways because it goes out to redshift 40 and it resolves halo down to resolution that no one else can. We need two things to help us answer that question. We need the halo mass function. This is halo distribution by mass as a function of redshift all the way out to 30. And then we need the halo accretion rate. This is how quickly halo can accrete gas onto them from the universe. And with the little toy model this time, not a SAM, we just make a few very simple and reasonable and quite widely adopted jumps. So we go from halo accretion rate to the star formation rate, assuming some star formation efficiency. There's no physics in there. It's just a efficiency, a percent that tells you how much of these accretion rate translate into stars. How much gas can fall onto these halos, become stars instantly. And from there, the star formation rate can be used to track UV luminosity using a McDowell-Dickinson conversion factor. This is pretty standard. And this is especially valid at this redshift because at redshift 17, these galaxies are dominated by young stars. These stellar populations are incredibly simple. They are just there. So the number is still okay. So what we're looking at on the left is the UV luminosity functions predicted with the toy model. And let me just bring this up. So what we're looking at here is the luminosity functions, and the right panel is the star formation efficiency as a function of halo mass. So the blue line there is what happens when we assume 100% efficiency. All the gas fall into the halo get turned into stars, which is not physical, but hey, for the sake of not breaking the universe, let's demonstrate that. At redshift 25, yes, we can make a bunch of galaxies out here. These are upper limits, so we don't have to match them strictly. But for these data points out here, yes, we can make them. We just don't know how to make stars that quickly, but there are enough baryons in there, so we just have to make it. And I want to further demonstrate that we don't actually need 100% actually. So what our colleague Contact Iyer did is we did a little MCMC fit. And the purple shaded region with the line over there on the left panel, the luminosity functions, are directly result from the fitted star formation efficiency from these right panels. So what we're looking at here is at redshift 12 to match the redshift 12 observed galaxy luminosities. All we need is roughly a few percent all the way out to maybe 20% for the most massive galaxies. And at redshift 14, nothing more than 40%. These are still reasonable. We can still reproduce those in a SAM, so we can still physically explain them. At redshift 17, things get a little more interesting. We still only need a few percent out there, but toward the bright end or toward the massive halos, we do need a little boost up all the way up to 60%, which is, some might say, unphysical. But I would say the bright end is also not really that sensitive to the star formation efficiency. It's just so unconstrained out here that the error bars are so big. So the efficiency can also be a huge range. So maybe it's just 20% is not that unphysical. Well, it's not too bad, but redshift 25, well, we don't really have constraints out here. That's why it's being represented in the fainter color. And all we have constraints for those measurements, if you believe those galaxies are real, it's just this tiny little halo mass range. But it's not unreasonable, 40%, it's not too bad. Out there, the upper limits are not being treated as rigorously, so it just, it blows up. So it can sweep this huge range. But out to redshift 25, the universe is still not broken. And we'll see if these are all real, maybe they're not. So that's not my problem at that point. Okay.
Consider realization at the same time.
At this time?
Yeah, realization.
Yeah, well,
About it.
From the IGM?
To realize the universe from this uniform.
Yeah, reionization hasn't happened yet.
You want more galaxy, more star, but you realize the universe.
Yeah.
It's not problem at all.
Yes, people have been talking about it. One of my colleagues have written a paper on it. I should write one too. In the conventional wisdom is that reionization doesn't happen not well below, but slightly below redshift 12, so at redshift 10. So at one point it became a problem where if all of these galaxies are real, we might have an ionizing photon budget problem in the opposite sense, that we might have too many ionizing photons and the universe could have reionized a lot quicker. But my counterpoint to that is at these redshift, the universe is so dense that the IGM probably recombine in a much quicker rate than redshift 10. So even though these galaxies existed, those ionizing photons wouldn't get too far. I mean, the light still get to us, so we can see them, but perhaps large-scale ionization wasn't happening so quickly. That's my guess. But of course, now I have all the ingredients I need to do the actual calculation, which I did before JWST was launched, and I just didn't have time to come around and do this. Great student project, though. If there's a student who wants to take that on at one point in the future. But thanks for that question. Okay, so I'm completely changing topic here without a transition slide. This is not related to the previous slide. We're done talking about redshift 30 sources. We'll talk more about them when we confirm that they're actually at redshift 30. Now I want to tell you about the project that I'm working on right now that I'm most excited about. And this is looking at the star formation history of galaxies. You see, I have been showing you the luminosity functions at different redshift. And these tell you how the bulk of the galaxy population evolved over time. It tells you how many galaxies have been building up as over the course of redshift 17 to 14. But there's no way to tell which galaxy evolved into which. When I look at a luminosity function and point at some point out there, a minus 16 luminosity, magnitude minus 16 galaxy at redshift 17, I have no idea where the galaxies would end up at a lower redshift point in time. Or the vice versa, if I look at a galaxy at redshift 6, a bright galaxy, I cannot tell at redshift 15 what would be that galaxy's progenitor. And quite frankly, we have not been doing that enough in simulations. You can do this in observation. This is how the universe is set up. We can see into the past, but we can't see the universe play like a movie. We're too short-lived. So we can do this in simulations. Combining GRAPH and the SAM, I can now map out the stellar mass assembly history of all my individual galaxies as a function of the age of the universe, or redshift. So each of these individual tracks represent the mass throughout the course of their evolution, and they're color-coded by their mass at the terminal redshift, in this case redshift 6. So they're nicely organized at redshift 6, color-coded by their mass at this point. But as we go further and further out, we realize that the most massive galaxy is not always the most massive galaxy. Maybe that one is extreme, but you can see that. Here, things get really messy. The lines do cross. There are galaxies that form later, but build up their mass a lot quicker and end up here. But same for the galaxy end up in the same mass. You can also have a slow grower that form earlier, but build up their stars more gradually and still end up somewhere. So that's something that really interested me. I have created a bunch of these star formation history plots, or we also call them galaxy stellar mass assembly history plots. So this is really busy, but I'm taking the same plot you saw earlier, and then I'm binning them by their terminal stellar mass. So this panel on the upper left are all the galaxies that ended up in a 10 to the 6 solar mass galaxy, and then these are 10 to the 8 solar mass, something like that. So let's just take a look at one panel to make things simpler. You can see galaxies that end up at the same mass at redshift 6, 12 in this case, can take very different evolution course. We have something that goes really fast, something that, these guys are, fast in terms of when they start building stars, but also grow relatively slowly. But we can also have galaxies that do not do anything for a long time, and then suddenly they form stars, which is very interesting. Now I can characterize them by this quantity called T90, which is the point in time where beyond which they forms 90% of their stars. Same with T50, which is the point in time that it takes to form half of their stars. And you see this little nice distribution. It characterizes how galaxy at this mass, how long would it take to build up their masses. And if I organize this into a heat map, I find something even more interesting. For a redshift 6 galaxy, let's say they're 10 to the 9 solar mass, this galaxy would take a typical time scale T50 of 128 mega-year to form half their stars. These are median numbers, so it varies a little bit. But for redshift 6, these galaxies are relatively slow. But if you look at a redshift 10 galaxy of the same mass, they form half of their star in just a third of the time compared to their redshift 6 counterpart. So looking at this, I start to think maybe looking at early universe galaxy as analogs. Looking at low redshift galaxies as analogs of the early universe galaxy is not the right way to do this. At least it has to be done through a more stringent selection criteria or something, because these are fundamentally very different star formation histories, even though they're the same mass. You can also see that out to redshift 15, it takes just 15 mega-years to form half their stars. I don't have these massive galaxies out here, but you can see that the time scale really is about 30, 40 mega-years somewhere here for these galaxies. And that poses another big problem with both the simulators for us, right? Is our model resolving star formation at such short time scale? If our star formation has a time resolution of 10, 30, 40 mega-years for each time step, then we're not really capturing these activities. We're quite screwed. But also for people who does SED fitting, is the template capturing the contribution of these young stars. Are the templates that we use to extract the physical properties of redshift 13, 14, 15 galaxies, are they good enough? Well, we have been doing that for years for redshift 6 to 10 galaxies. These are fine because star formation are spread over a longer period of time. But for this redshift range, star formation is so rapid and the young stars are so dominated that we really need the templates to reflect their contribution. So that's something for us to think about. So almost there. Wait, is it? What time is it? I think I'm
Almost.
past the hour, shoot. Anyway, so what I'm really interested in now is really connecting the galaxies to their progenitors, right? So for example, with galaxies that end up at redshift 6 somewhere, these are all the possible tracks. So that would be interesting thing to put out there for the observers to consider and build a framework to connect the galaxies that we observe along the way. They're not exactly the same galaxy as we observe to the higher and higher universe, but we want to figure out which galaxy would be the most probable progenitor of these galaxies. But the same thing happens the opposite direction, right? We have a galaxy that can be relatively low mass at the early universe, but what would they become down to the lower redshift universe? That's another interesting thing to think about. All right, so I guess I need to stop here. And I'll skip over everything else and get to my conclusion. Roman is important. And so many student projects. Anyway, thank you.
Any question for Aaron?
Yes.
So is this density modulated star formation model? You can reduce the number density of galaxies. But I think you also believe IMF should evolve.
Yes.
So you also implement that.
That's a conversation killer right there. You don't do that in the conference. Just kidding. So it's more complicated than that because while the IMF actually doesn't do much to the SAM, but it does more to the SED. Now the SED template, the simple stellar population models, they all rely on the IMF they put in. They sort of take that as input. But we don't generate that in-house, and quite frankly out there all the nice models that we're using like BPAS, they gave us a few options, but none of those really resemble a POP3 star IMF. So, and let's say if we even implemented those, there's not really ways to tell if those IMFs are actually correct. So please observe them and let me know. Is that a good way? Shove it out of the way. I mean, it's really helpful to have more observed constraint on the IMF before we go wild and do whatever we want. Yep.
Yeah. So you mentioned this bursty star formation as an explanation of this ultra bright galaxies. But why do they systematically bias high? I mean, supposedly you have a scatter. They can also be like very dim.
So it actually goes both ways. You're right. So I wish I had explained this a little more clear, but thank you for asking. So when you look at luminosity function, the proper way to think of these is actually these are histograms. These are bars, right? So you can imagine if I put in a scatter to a certain bin to this galaxy, that bar will become a Gaussian distribution or something like that. It will become a distribution, some sort of bell-shaped thing. The problem is for galaxies that are moved left, they disappeared. These bins are huge. There are a lot of galaxies anyway. Adding one to a bin to the left doesn't change anything. But if I add one to the right, now these numbers are small. This is log scale. So by moving a good portion of galaxies toward the right, that can really boost the number count in the brighter bins. And that's why. I think this is called Eddington bias, but maybe there's another name for that. Yeah, but thanks for asking.
Related question. You play around with the baryon sector. Do you think we can also play around with the dark matter sector?
Good question.
To help run the CDM?
Yeah, well, we are a little passive in that sense, right? Because the SAM, the modeling technique, take dark matter mass assembly history as input, so we have very little to say. But it does worry me, or sometimes keep me up at night with jet lag. So the problem is with graph, we're probing down to the scale that is so small, the mass range, mass scale that is so small that the halo density profiles start to matter, or the nature of dark matter would come into play. So that would actually potentially impact some of these predictions. But so far, there's no strong evidence that tell me that dark matter is doing something fundamentally different in the real universe and then in our simulation. So hopefully we're okay for now.
Okay.
I'm curious, why is there any deeper physical understanding on why excursion set theory failed?
Well, it doesn't fail actually. It should work. The problem is at redshift 15, these galaxies are not forming at the boring places, the cosmic average density regions. These are actually forming at regions that are dense and collapsed earlier. Now, EPS doesn't have the ability to capture that, right? It assumes the distribution of dark matter halo by mass is, assuming a cosmic average density, matter density. And that's a problem.
I thought, let's see, there's a distribution of overdensities, and then I guess, is it true that you do have less halos compared to I guess unbodied results?
No, but so if you look at a big enough box, the number will still work out. But the problem is the mass assembly history. We're looking at some of these merger trees that are rapidly merging and forming kind of earlier than the rest of the universe, right? These are where things start to collapse before the cosmic average density environments. So that's one thing. And another thing is our implementation of the EPS tree also have its own internal time step. So it comes down to, at the end, a time step problem, kind of like what I show you in the illustrious TNG scenario, where we have sparser and sparser snapshots out to higher and higher redshift. So
that should be very cheap to fix.
yes, but we went a little fancier than that. So instead of doing that, we came up with something that is a little more physics-based, or we use machine learning basically. We learn from these 4 boxes, from this tree sample, how halo emerge. And then using a neural network, we can now generate trees, kind of like a replacement for extended press ejector. But we also account for some environmental effect that is encoded into a halo. For example, their concentration, their spin, which is a few things that extended press ejector doesn't really account for. But now we can generate trees that also account for these different halo properties, and voila, we have a distribution of trees that kind of, more they're closer to the n-body simulation trees.
Yeah. And Satoki?
You mentioned about the high intense star formation that you needed to estimate explain the high Z equal 14 or something, which means that you need a really reasonable amount of molecular gas should be there. Right?
Well, so in the SAM that I've been working with pre-JWST, we switched over to use molecular gas as a tracer that is motivated by the work from Begill et al. That is based on observation and things like that. Now, the problem with that is we know this relation breaks down at early and early universe. Molecular hydrogen is, well, first, we use metal as a tracer for molecular hydrogen, and that no longer correlates well in extreme environments, right? As metal gets poorer and poorer, well, as the galaxy gets more and more metal poor, the metal no longer attracts molecular hydrogen. And molecular hydrogen is just not physically a good thing to track star formation. There's nothing connecting the two. So that's why actually in all the comparison, we switch back to use Kenneketter-Schmidt as our baseline model to compare to for our cloud-based model. But yeah, we still don't know how star forms, do we?
Can you actually observe, like maybe almost too high frequency, NJBLA or something to detect those kind
Yeah, I think we talked about this yesterday briefly with Ting Wen. So it's important to come up with ways to test these cloud models, right? Right now we're just able to reproduce the number density in a very coarse way. But we don't have the individual galaxy properties. We don't have the distribution of metal and all the other things for us to test the model. So cycle 5 is happening. We proposed something. We asked for a few hundred hours. We'll see if that gets through, but yeah, we have plans to actually test it. Yes.
Okay, since time's up, so Aaron will stay in ASIAA for also on the tomorrow. No, not tomorrow, but
Friday. I'll be here all Friday.
So you are welcome to check with him at his office at 11th floor. So let's thank Aaron's talk again.
Oh, by the way, I brought you guys some posters.